Good day. The title of our paper is Development of Arithmetic / Logical Computational Procedures, Computer-Aided Digital Filter Design with Bilinear Transformation. My name is Dr. Abdul Rasak Zubair. My colleague is Adeolu Johnson Olawale. Filter basics. A filter is a frequency selective network. In signal processing, at times it is necessary to select a desired signal from a mixture of available signals. It can be analog signal processing or digital signal processing. For example, a radio receiver will have to select a radio station out of many radio stations. A signal has a frequency or a band of frequencies. A filter passes a range of frequencies. This range of frequencies are known as called pass band. A filter blocks a range of frequencies, and this is referred to as stop band. There is ideal and there is practical. There is an ideal filter, there is a practical filter. This diagram is showing us the frequency response of an ideal low-pass filter. You have the pass band, you have the stop band. In between the two, we have what is known as transition band. The ideal low-pass filter cannot be realized using components like capacitor, resistors, and other circuit components. So this leads us to what we call approximation function. An approximation function provides a realizable frequency response, which is approximate to the ideal frequency response. We have 5 types of approximation functions: Butterworth, Chebyshev, inverse Chebyshev, elliptic, and Bessel. Filter design. When we talk of filter design, we mean calculation of filter coefficients. Digital filter design is an active area of research in electrical and electronic engineering. There are a number of complex approaches. Some use optimization techniques. Some use tedious approaches, which involve the use of extensive tables coupled with manual expansion and computations. In this work, a simple approach is developed. In this approach, we are using mathematics and programming to solve a problem in electrical and electronic engineering. Methodology. From first principles, we can design what we call normalized analog low-pass filter. From this normalized analog low-pass filter, we mean that it's a low-pass filter and the pass band edge frequency is 1 rad per second. From this filter, we can get other filters, like the analog low-pass filter, APF, analog high-pass filter, HPF, analog band-pass filter, BPS, analog band-stop filter, BSF. From this analog filter, we can go to digital filter using a bilinear transformation. In this work, we observe patterns in the manual expansions and computations. These patterns are converted to arithmetic and logical operations and logical computational operations, and these are coded into computer programs. Here we have low-pass filter, we have high-pass filter, band-pass filter, band-stop filter. For the low-pass filter and high-pass filter, you need only one cutoff frequency, which is omega c. For the band-pass filter and band-stop filter, there are 2 cutoff frequencies, omega c1 and omega c2. Now, in this work, we carry out substitutions. We have manual attempts, we study patterns which are converted to arithmetic logical program. Now, we have 3 transfer functions here. Equation 3 is for normalized analog low-pass filter. Equation 7 is for low-pass filter. Equation 13 is for digital filter. When we have normalized analog low-pass filter, we can make these substitutions into it to give us analog filter. For example, if we want a low-pass filter, is equation 8. Substitute equation 8 to this. If you want high-pass filter, substitute equation 9 to that. If you want BPF, substitute equation 10. If you want BSF, substitute equation 11. And that will lead to the analog filter. From the analog filter, we use bilinear transformation, equation 12. We substitute it into equation 7, and that will lead us to equation 13, which is the transfer function of the digital filter. Here, we see that S is equal to J omega, Z is equal to E raised to power J omega, and the gain of the filter is indicated here. This is for analog, this is for digital. Now, when we are converting analog to digital, put it in mind, when we have analog frequency, omega C is analog frequency, omega DC is digital frequency. We can convert digital frequency to analog frequency. We can also convert analog frequency, omega C, to digital frequency. Let's now take the different filters one by one. We have the analog low-pass filter. We start from, we have the normalized analog low-pass filter. The W pass is 1 rad per second. The user will select these quantities. And then the user may want negatively high band stop gain, which is A stop. The higher the A stop, the better the filter, the higher the order of the filter N, and the more complex and the more costly it is. Another trade-off is narrow transition band. Between narrow transition band and the wider transition band. Narrow transition band is better. It will require a higher order. The user will have to select an approximation function. The software will calculate the order N based on the quantities given, except for Bessel function. In this case, the user will have to suggest N. There are equations in the references, especially reference 4, which gives the poles and zeros, the gain constant K, the polynomials, numerator polynomial, poly NF, denominator polynomial, poly DF. So with this, the normalized analog low-pass filter can be easily obtained. After obtaining the normalized analog low-pass filter, we move to analog low-pass filter. In this case, don't forget, we are going to substitute equation 8. When we carry out the substitution, this is the numerator polynomial. When we substitute equation 8 into it, we are going to have this. Multiply through by omega C raised to power N. That's going to lead to this. And by the time we compare this with this, we are going to see that the coefficient of the analog low-pass filter is related to the coefficient of the normalized analog low-pass filter with this expression. Now, this multiplication through by omega C raised to power N will cancel out when we repeat this step for the denominator polynomial. The observed patterns in these steps 2 and 3 are converted to arithmetic stroke logical computational procedures, which are coded into a computer program. The filter order remains as N. Analog high-pass filter, we repeat the same process, and we are going to get the observed patterns, which we are going to convert to computer program. Note here that the substitution for high-pass filter is reciprocal of the substitution for low-pass filter. Now let's go to analog band-pass filter design. In this case, we are having 2 pass band, 2 cutoff frequencies. So this is the expression to substitute. And by the time we have this substitution, when we expand this, when we expand S over G plus P, when we expand this, it will lead us to what we call table 1. Table 1 can be seen here. When we expand raised to power 0, 1, 2, 3, 4, we are going to have this. Definitely there are patterns here which can be exploited, So with that pattern, we can see that for any given M, the coefficient of the normalized filter will contribute to all the coefficients, to some of the coefficients of the analog bandpass filter. So these are also converted to a computer program. The next is analog band stop filter design. The substitution is equation 11, and it is reciprocal of the one we use for analog band pass filter. And then we are going to have this, which is similar to what we have for band pass filter, except the other. This is from 0, 1 up to n, whereas this is from n to 0. So which means the band stop filter design resembles that of a band pass filter. So the computer program for the band pass filter can be adjusted slightly to form the computer program for the band stop filter. The order of the filter is 2n. Digital filter design. For the digital filter design, we take the analog filter, we convert to digital filter using the bilinear transformation, which is here. There are patterns. There's also a table like this that suggests what we are going to, the expansion. So these patterns can also be programmed easily. So in this work, a software system for digital filter design has been made. It's a filter coefficient calculator. It can plot post-zero diagram for the normalized analog low-pass filter and for the other filters too. Tests and results. Digital band pass filter is the first one. When we are giving this input for the normalized analog low-pass filter, an elliptic approximation function is selected, and the elliptic approximation function is selected, we have the following results. We got the order of the filter to be 7, but for the normalized analog filter, but for the band pass filter, it is 14. We have the transfer function for the analog normalized low pass filter. This is for the band pass filter. This is for the digital band pass filter. This is analog. And we can see the frequency response. Frequency response for normalized analog low pass filter, frequency response for the analog band pass filter, frequency response for the digital band pass filter. We also experimented with high pass filter. We are giving the necessary inputs. We have the outputs. In this case, the order is 5. And then the analog high pass filter, in this case, we have the same order. So we have, this is the transfer function for the analog normalized low pass filter. This is the transfer function for the high pass filter. And this is analog. This is for digital. And these are the frequency response. Normalized low pass filter, analog high pass filter, analog digital high pass filter. So here also we have a band stop filter. In this case, inverse Chebyshev approximation is selected. We have inverse Chebyshev is such that there will be ripples in the pass band and the stop band will be flat. So we have response for the normalized low pass filter, response for the band stop filter analog, response for the band stop filter digital. Manual calculation is easily handled for order 1 and 2. Manual calculation for order 3 and above is not convenient and is prone to human error. With this software, calculation for higher order is made easy and error-free. The development of a software system for the computation of filter coefficients has been presented and tested. Analog and digital filter design has been made simple. Test results and frequency response plots confirm the accuracy of the arithmetic stroke logical computational procedures deduced from the patterns in manual computations. The software is recommended for use in electrical and electronic engineering practice. References. Thank you.